Thanks for inviting me, and thanks for staying around to the last day. Yeah, so this is relative error tensor low-rank approximation, joint work with Zhao Song and Peilin Zhang. I realize this is a pretty diverse audience, so please stop me if there are any questions. OK, so what is a tensor? A tensor is just a multidimensional array. So here's a cube. It's a third-order tensor. You have parameters to describe a tensor. OK, so you have some order q, so it's 3 here. And you have a dimension for each direction of the tensor. OK, so n1 through nq. Maybe this is an n by n by n tensor. Yeah, so q equals 3 is a cube. Q equals 2 is just a matrix. Q equals 1 is a vector. And let's just set up some notation for this. So let's call these vectors columns, these vectors rows, and the vectors into the screen tubes. And we can also look at things like column-row faces. So we can take columns and rows together, and we get a face of this cube. We can look at row-tube faces and tube-column faces. OK, so what we're going to look at in this talk is generalizing a lot of linear algebra problems and machine learning problems that have been developed over the years for matrices to tensors. OK, so let me first say what's known about matrices. So let's look at the low-rank approximation problem. So suppose we're given an n by d matrix A and a rank parameter k, and some accuracy parameter epsilon. Then what we might like to do is to approximate our matrix A with a low-rank matrix, A hat. OK, so A hat is going to have rank k. And what we'd like is that if I look at A hat minus A, it's small under some norm. OK, yeah, so in particular, what we'll look at is the Frobenius norm, which is the Frobenius norm of a matrix is just the sum of squares of the entries to the 1/2. What we'd like is to find this rank k matrix A hat so that the difference of A hat and A under this norm is pretty small. Say it's at most some approximation, 1 plus epsilon, times the best possible approximation of A by any rank k matrix A prime. OK? Yeah, so again, we're just looking at Frobenius norm here. Any rank k matrix can be written as the product of two matrices U and V. So U is n by k, and V is, say, k by d, if A is an n by d matrix. And so you want to find these factors of your low-rank approximation. There are many motivations for computing a low-rank approximation. Instead of storing this big n by d matrix A, I can instead store these two factors, U and V. So my number of parameters, instead of being, yeah, question?
Does Frobenius norm nearness say anything about the behavior of the linear the systems associated with?
Yeah, so I'll mention a variety of different norms here. Frobenius norm is the main example we'll focus on. But yeah, if you have a small Frobenius norm, a small enough Frobenius norm, then if epsilon is 0 and this is actually a rank k matrix, then you'll recover the rank k matrix. But yeah, there are other norms that are better in certain situations. Yeah. So a nice thing here is you get a parameter reduction, right? Instead of n d parameters to represent A, you just store U and V, which is more like n plus d. So it's n plus d times k, and k is supposed to be this small integer if you're doing low-rank approximation. Another nice thing is you can multiply your matrix A times a vector very quickly, right? Instead of spending n d time to multiply by a vector, I spend like dk time to multiply by a vector, and then nk time to multiply by that output times this. So I can multiply in roughly n plus d time as well. And a lot of matrices in real life, they actually are close to low rank. They might only not be low rank because of some noise, measurement noise, or or whatever. And what you can think of low rank approximation as denoising your matrix. Okay. What?
PCA they call it usually, right?
Yeah, so PCA, for example. Okay, so you can solve, over the years, people have developed randomized algorithms for finding these factors u and v. And what we know now is we know how to find such factors u and v very quickly in time, which is n in z of a. So n in z means number of non-zero entries of a. So it's sensitive to the sparsity. Oftentimes, your matrices are sparse. N in z of a plus what's typically a low order term, n plus d times polynomial in k over epsilon. Okay, epsilon approximation, rank k. Okay. Any questions? Okay. Okay, so you could ask the same question for tensors. We have all these results for matrices. What about the following questions? Suppose I have a third order n by n by n tensor A, again a rank parameter k, and some approximation factor alpha. And what I'd like to do is I'd like to output a rank k tensor A hat. Now, I didn't say what rank means yet for tensors. Hold on to that for a second. But suppose there's some notion. I'd like to output a rank k tensor A hat such that the norm of A hat minus A is small. And Frobenius norm here still makes sense, right? Frobenius norm was just sum of squares of entries, of differences of entries. Why can't I ask the same question for tensors? Sum of squares of differences. So I'd like to output an A hat so that the Frobenius norm of A hat minus A is at most some approximation factor alpha times the best possible approximation to A by any rank k tensor A prime. Okay, so so Frobenius norm is the same here. Let's just call this quantity opt. So we want to output something with cost alpha times opt. Okay, so then the first question is, what is the rank of a tensor? So there are multiple notions of rank, and the main notion we'll focus on in this talk is what's called the canonical or CP rank. So what that is one way of defining the rank of a matrix is just the minimum number of rank 1 matrices I need to add up to get to my matrix. Right? So I'm taking the outer product of two vectors, and I get a rank 1 matrix, and I'm adding them up and getting my matrix. That minimal integer is the rank. And you can say the same thing for tensors. Right? I can take 3 vectors, and I can take the outer product of these 3 vectors. I get ui cross vi cross wi. I'm going to call that a rank 1 tensor. And I'm asking what's the minimal number of these I have to add up in order to get my given tensor. That's its rank. Okay? Okay. Let me just write the tensor in a slightly different form in terms of matrices. So instead of this sum of outer products of vectors, let me write it as u cross v cross w, where u is n by k. It's a matrix. V is n by k, and w is n by k. And this just means exactly the same thing as before. So what this operation means is I take the first column of u, I take its outer product with the first column of v, and outer product with the first column of w. That's one rank 1 tensor. And then I add that to the outer product of the second column of u, outer product second column of v, outer product second column of w, etc. Okay? So these are the factors, the analogous factors that I want to find in the tensor case. Yeah, question?
So for an n cross m cross k matrix or a tensor, what's the usual rank for a generic such tensor? What's the usual rank for such a tensor?
For an n by n by n tensor, if I take a random n by n by n tensor, this would be around n squared actually. So so let me get back to that. Yeah, so it's larger than n. Yeah. But we don't know how to construct explicit tensors of rank larger than n. Yeah, much larger than n. Yeah. Any other questions? Okay. So so this has all the same motivations that we had before, right? We'd like to reduce the number of parameters. We don't want n cubed parameters. We want roughly like 3nk parameters. You can also apply this more quickly to a vector. We can denoise a tensor, etc. Same motivations. Okay. So so before getting into that, let me just mention, going back to a question in the audience, there are many other norms you can look at for both matrices and tensors, right? Instead of Frobenius norm, you could ask, can I find a rank k matrix, these two factors, u and v, such that some norm of UV transpose minus A is the most alpha times the best possible norm for any rank K matrix approximating A. So the norm could be this Frobenius norm that we talked about. But in other applications, it might make sense to do something like the entry-wise L1 norm. So instead of the sum of squares of differences, maybe we just want the sum of absolute values. This is often considered more robust, because if you have some grossly corrupted entry, then you're not paying as much attention to it, because you're not squaring it. And so you're paying more attention to the remaining data. This is the intuition. There are also other notions of robust measures, such as sum of L2 norms. So instead of taking the sum of squares of all the entries, I take the Euclidean norm of a row, and of each row, and I add up all these Euclidean norms. This is also more robust, and it has a nice geometric interpretation. So the SVD, the singular value decomposition, is trying to minimize Frobenius norm. And what you can think of that as doing is trying to find a low-dimensional subspace which minimizes the sum of squares of distances of all your rows of A to it. Okay, you're trying to find this low-dimensional subspace, and thinking of the rows of A as points, you're trying to minimize the sum of squares of distances to this low-dimensional subspace. And what this more robust thing is doing is it's trying to find this low-dimensional subspace which just minimizes the sum of distances of the points to it, which, since you're not squaring things, is often considered more robust. And so other things you could look at are like weighted Frobenius norm. Why should all of the entries of A contribute the same amount to the objective function? This is useful when you want to sort of renormalize some entries by their variance. Like maybe some entries are more corrupted than others. Matrix completion is also a special case of this, where the weights are 0 and 1. I want to mention for all the results cited here, we make no assumptions on the matrix A. So these are for worst case matrices. And we get input sparsity running time, n in Z of A. These problems, other than the Frobenius norm, are all NP hard. The approximation ratios, they're not going to be something like 1 plus epsilon that we were talking about for Frobenius norm. They'll be a bit larger, like polynomial in this rank parameter k and log n, for example. But OK, so there are many more norms we can look at. And we can also look at all of these in the context of tensors. I don't really think I need to motivate tensors to you guys, but there are tensor data sets everywhere. For instance, everywhere you have, for instance, a three-dimensional array, maybe Facebook wall posts. You have some wall owner. You have someone who's posting on this wall. You have some time of day. And the corresponding entry in the tensor is the number of posts made. Yeah,
last primary question.
Motivation for tensors. OK, so let me do this motivation. But sort of anywhere you can think of a three-dimensional array. So
actually, the question was, is there an analog to eigenvectors?
For general tensors, no. Yeah. So there are things called like orthogonal tensors where you can have analogs, but in general, no. Yeah. There's no like SVD or anything like that for tensors. Yeah.
Question. You mentioned the NP hard in the previous slide. So the lower bounds to this, I mean the log n and everything is already tight lower bounds.
The approximation factors are not known to be tight. There are NP hardness results, but they don't match the corresponding upper bounds. Yeah. But the question wasn't about motivate. Well, OK, let me just motivate this. I mean, maybe Enron has employees that send emails to each other at certain, and inside of 1 month, you might want to know how many emails have been sent. Tensor data sets arise in these never-ending language learning project at CMU, where you look at pairs of words in some contexts, and you look at number of co-occurrences. Network data where you have packets. And you have source, destination, maybe port number, and you want to know the number of packets between those entities using that port. So you have very large tensor data sets. A lot of these are occurring in real time, like network traffic, and you'd like to be able to approximate these. OK, so the main question here is that we're looking at is, and I'm going to focus on third-order tensors, and just for simplicity, assume they're n by n by n. So given a tensor A, is there an efficient algorithm to output this rank k approximate tensor A hat which gives me a good approximation in Frobenius norm. So the Frobenius norm of a hat minus a is at most some approximation factor alpha times the best possible cost under any rank k tensor. Or are there any inapproximability results? And what about all these other norms that we looked at for matrices? OK, problem is clear. All right. So this natural notion has not really been studied. Maybe you can tell me a few reasons why. So there are multiple problems with this problem formulation. OK. Well, OK. So yeah. So no algorithms achieving this guarantee have been proposed. So first of all, there's something a little bit peculiar about tensors. But it doesn't really stop any algorithm from being proposed. The rank of a matrix is at most n, but as someone asked, the rank of a tensor, in this case a third order tensor, can be as large as n squared. But why does that really matter for an algorithm trying to achieve this guarantee? So any thoughts on why this might, why this notion hasn't been proposed? Do you think that this can be done efficiently?
The measurement can't be done efficiently, but the algorithm will be efficient.
OK, so I just give you this n by n by n. What?
Already compute the rank or something?
Yeah, exactly, right. So computing the rank of a tensor is already NP hard.
So what?
To approximate?
Well, OK, so let's look at the notion we're claiming. We're claiming that we can get a relative error guarantee, right? So if I can get a relative error guarantee, what I can do is I can set k to be equal to 1. I can see if my cost is 0. Set k equal to 2, see if my cost is 0. I can figure out the rank of a tensor from this relative error guarantee, right? It's the first time that this cost is becomes 0. So OK, yeah. So computing the rank of a tensor is NP hard. Hastad showed this. OK, so that's one problem. So there's not going to be an efficient algorithm for this notion. But there's actually an even more fundamental problem with this formulation, which is that this is not even a well-defined quantity. This minimum over rank k tensors ak of the norm of ak minus a, this actually might not exist. Yeah, so let me get into that. So the best rank k solution might not exist due to what are called border rank issues. This doesn't happen for matrices, but it happens for tensors. And let me say what that means. OK, so again, the rank of a matrix, as we said, is just the smallest k. So I can write it as the sum of k outer products, k rank 1 matrices. And we had that same analogous definition for tensors, sum of k outer products. Let me introduce a new notion called the border rank of a tensor. The border rank of a tensor is the smallest integer k such that there exists a sequence of tensors of rank at most k whose limit is a. OK, so I'm taking all these, the border rank is k. I'm taking the smallest k so that there's some sequence of tensors which gets closer and closer to a.
Why did you change the story? Why can't we continue with just 4 matrices and so on?
OK, so I defined the rank of a third order tensor. And now I'm defining the border rank of a third order tensor. OK, and I'm going to show that the border rank can be smaller than the rank. So let me show you an example. OK, so consider 2 vectors u and v. They're unit vectors, and they're not equal to each other. And let me define the following third order tensor A. The details are not important, but let me just say them. So it's u cross v plus u cross v cross u plus v cross u cross u. You can show the rank of this tensor is 3. OK? It can't be expressed as a smaller order, a smaller ranked tensor. However, A can be approximated arbitrarily well by the following sequence of rank 2 tensors, which I'll index by Bn. Okay, so n is going to infinity. Again, the details are not so important, but what Bn is it's some rank 1 tensor minus some other rank 1 tensor. Okay, so its rank is at most 2. And I can re-express this just by manipulating this expression as A plus 1 over n times some bounded norm tensor plus 1 over n squared times some bounded norm tensor. Okay, this is just taking this rank 2 tensor and writing it in a different way. So A plus 1 over n times something plus 1 over n squared times something else. And the thing is, as n is going to infinity, this B sub n is getting closer and closer to your tensor A. Okay, it'll never reach A. I mean, the limit is not going to be realized. Right? I mean, A is a rank 3 tensor, and these are rank 2. But you can see that this causes a problem in the definition that we had for low rank approximation of tensors. You know, I ask you, what's the best rank 2? Give me the best rank 2 approximation to this tensor A. What are you going to give me? You're going to give me some rank 2 tensor it's going to have some cost. I can just give you a much better rank 2 tensor by going farther along in this sequence. So there's no way you can get a relative error guarantee, right? It's not the minimum is not even defined, right?
Just limit the size of the sequence, no? I mean, you can add another limitation to solve this, no?
I mean, there are ways of dealing with this, like with things like bounding the bit complexity of your approximation, etc. But yeah, in general, that notion has problems. One fix that we'll do here is if you just add an arbitrarily small additive error here. Now, this additive error can be an arbitrarily small function. So like 1 over n to the n to the n. I mean, whatever you want here. That'll fix this issue. But that needs to be there to handle these border rank issues. OK. Any questions? Yeah, Eric.
What if you made it be, you could output a rank 2k tensor?
Output something with rank larger than k. Yeah, so we're actually going to, so a Bicriteria solution. Yeah, so
would you still have border rank issues?
We have border rank issues. Let's see. So, so one thing about this is that this is not just this border rank is not just rank versus rank minus 1. This can be like rank versus anything less than rank. So I think because of that, there might.
It's already like 2/3 the rank. Right?
I mean, you could have something which is rank k, and the border rank could be like 2 or something. And then I think there would still be problems. Yeah, but let me think about that. Yeah. Any other questions? OK. Yeah, but Bicriteria solutions is one way we're going to deal with NP hardness, by the way. So OK. Let me get into our results then. So algorithmically, we'll give a Bicriteria solution. So this is OK because it's still well motivated. We're going to have a significant parameter reduction, which is one of the motivations. If you insist on a rank k tensor, then what we're going to do is give you an algorithm which is efficient when k is not too large. Okay, so it's going to be in this realm of parameterized complexity. You can think of it as being fixed parameter tractable in terms of k. We'll also give a special kind of algorithm called a if you're familiar with column subset selection algorithms for low rank approximation of matrices, we'll give the analog for tensors. These are called column, row, and tube subset selection algorithms. And we'll also mention some computational hardness, which suggests, which shows that some of the terms in our algorithm are actually necessary. OK, so let me just mention the main Bicriteria algorithm first. Again, focusing on third order n by n tensors. What we can show is the following. Instead of outputting a rank k tensor, we're going to output a rank r tensor, where r is order k squared over epsilon squared. Okay? And the guarantee, yeah, so I'm outputting these three factors, u, v, and w. They're n by r. The guarantee is that the cost of approximating A by u cross v cross w is at most 1 plus epsilon times the best cost if I were to use an actual rank k tensor. Okay? And it's a randomized algorithm. And the running time is very fast. So it's number of non-zero entries of A plus n times a polynomial in k over epsilon. Okay, I mean, so not only is it polynomial time, but it's actually optimal time up to this low order term, because you do have to read all the non-zero entries of a tensor to get a low rank, to get any relative error. Okay, so there's some blow up here. Instead of rank k, it's rank k squared over epsilon squared. Any questions? Okay. If you insist on a rank k tensor, then we also have an algorithm where we output, u cross v cross w. It's rank k now. And randomized algorithm. The running time, now the problem is NP hard. It's not going to be fully polynomial in all the parameters. So what happens here? We get the same running time as before, n in z of a plus n times poly k over epsilon, plus a term which is exponential in k squared over epsilon. Okay, so just some comments about this. So it's fixed parameter tractable. I mean, even if k is as large as like square root log n, we still get a polynomial time algorithm. And often in these applications, k is it's typically small. Okay, so okay. Let me mention this column subset selection algorithm for tensors. But before doing that, let me just say what it is for matrices. So if you haven't seen what's called the CUR decomposition, this is a special kind of low-rank approximation where the factors, these low-rank factors, consist of actual columns, subsets of columns, and subsets of rows, a subset of rows of your matrix. So given this M by D matrix A, we want to output three matrices. C, it's a small subset of columns of A. R is a small subset of rows of A. And U is just some arbitrary tiny connecting matrix, so that C times U times R has the right dimensions. Typically, you want U to be rank K. So C is going to have slightly more than K columns. R will have slightly more than K rows. But if U is rank K, this will still be a rank K approximation. And the goal is just for this to be a good rank K approximation. So the cost of using CUR is at most 1 plus epsilon times the optimal cost. The nice thing about this is that since your factors consist of actual subsets of columns or rows, if your original matrix had sparse columns or rows, for example, then your factors would be sparse. This also gives you some interpretation of what the factors mean. Maybe these are the important columns, etc. A natural question is how many samples of columns and rows are needed here. What we showed a few years ago with Boutsidis is that you can simultaneously get k over epsilon columns and rows. The rank of U is k. And we can do this in roughly n in z of a times a log factor. And there's also sort of a hard matrix, a matrix A for which you need simultaneously k over epsilon columns and rows. In this work, one thing we do is we improve this to sort of an optimal running time of n in z of a time. But what I would say is more important is what we do is we give the first analog for tensors. So for tensors, here's your n by n tensor. And what you want to do here is choose a subset of columns. So here's this matrix C. It's choosing some columns arbitrarily in this cube. So n by C, you should choose a small number of columns. You're choosing a small subset of rows here. Here's this matrix R. And a small subset of tubes here. Okay, here are the tubes that you're choosing. And just like for matrices, there's some connecting tensor, U here, which kind of glues these together and gives you an n by n tensor. And the way you can think of this is, so when I take my subset of columns, my subset of rows, and my subset of tubes, I take some column here, some arbitrary row here, and some arbitrary tube here, and I take the outer product of these three vectors. And I have some coefficient for that outer product in U. And I take a different triple, column, row, and tube, and I have some other coefficient in U. And U is just adding up all of these outer products. And so I mean, that's just what this notation indicates. And so what you can do is you can ask for a low-rank approximation of this form, and which is a 1 plus epsilon approximation to the low-rank problem. And you can ask again, how many samples of columns, rows, and tubes are necessary and sufficient for this problem? What we show is we first give a fully polynomial time algorithm, like input sparsity time. It doesn't achieve the optimal number of columns, rows, and tubes. It gets some polynomial in k over epsilon. Yeah, question?
Yeah, the question is, what is typical in this area to when one talks about a sparse tensor? What do we mean by a sparse tensor? Because a sparse means the number of non-zeros is proportional to n.
Okay, yeah.
Which you might think of if you thought of a configuration model or something like that.
Yeah.
Then the extra term seems to drown out the n and z, right? So.
Okay, so yeah, exactly. So yeah, if this is really exactly n, then our overall time would be dominated by this, and it would be n times polynomial in k over epsilon.
People agree it's a sparse tensor. Is it n or n squared?
I mean, so this could be as large as n cubed. It really depends on the application. I mean.
Sparse means something very interesting for matrices. So what does sparse mean in tensor speak, so to speak?
Yeah, I mean, I think it's really application specific. I mean, so you could have, yeah, I mean, so if k and epsilon if k over epsilon is not too large, this is sort of like order n. This is typical of sparsity of matrices. Yeah.
The number of non-zeros, what's an interesting regime for the number of non-zeros?
Yeah, anything less than n cubed, right?
I mean, I think anywhere between n and n cubed is, yeah.
That's the answer.
Yeah, okay. Yeah, so we don't get the optimal number of columns, rows, and tubes here. We get poly k over epsilon. And we don't actually find a rank k tensor U to glue these together. But it's polynomial time. If you really want the right parameters, like the optimal number of columns, rows, and tubes, you can get k over epsilon for all three of those. We can show that that's optimal. We can also find the rank k tensor U. But if we can find all this stuff, then we're getting some rank k tensor, which is approximating our input. It's achieving a 1 plus epsilon, a good approximation. And as I said, the best thing we know how to do in that case is to spend some exponential time in k over epsilon, k squared over epsilon. So we do have that additional term here. Yeah, and as I said, there is a hard instance which matches this. Okay. Questions? Yeah, Moses.
Can you design your benchmark so it also is forced to use something like this?
Design our what?
So your benchmark is the minimum rank K.
Oh, I see. So you want to, yeah, I've seen that's been done before. If you want to instead optimize over good column subset selection algorithms as opposed to actually rank K matrices. Yeah, I'm not sure. Yeah, so what would, yeah, I guess the question is like, what would happen to the complexity in that case, right? Yeah. Well, no, sorry. I mean, we do know I see. So it also depends on the parameters that you put here. Like, if you put k by k by k, you're saying. Yeah.
Would that be better?
Yeah, I'm not sure. Yeah. Even for matrices, I'm not exactly sure what the answer is there. Yeah. Yeah. Question.
So in AX, we have normal AX minus B sample generalization, which is very similar. Is this the case here? So if you want, so in SVD we have normal AX or normal AX minus B, but it's very similar problem. Linear regression, I mean.
Oh, regression. Yeah.
Analog here, analog version for this matrix.
Yeah. I mean, one thing you mean solving tensor regression, or?
Yeah. Kind of.
Yeah. I mean, so there are algorithms.
Same? I mean, like in SVD PCM, generalization is.
No, it's not trivial. Yeah, but yeah, let me get into the algorithm. And yeah, okay. hardness. So I want to try to justify some of these exponential running times that we have. So we can strengthen Hastad's hardness result using modern technology. So if someone gives you this n by n tensor and a rank parameter k, which has rank k, and you want to figure out what the rank is, so you want to output a number t, which is not exactly the rank, but it's at least the rank, and at most a fixed constant times the rank for a certain constant, then we can show, assuming the exponential time hypothesis, which this means that 3 satisfiability on instances of size n takes 2 to the omega n time. Like you basically can't do anything than just trying all assignments. If you make this standard complexity assumption, then we can show that to solve this problem, you actually do need to spend roughly 2 to the k time. Okay, and there are other complexity assumptions. There are randomized versions of the exponential time hypothesis due to Feige. If you make those assumptions, you actually get, you can't solve this problem in less than 2 to the k time. Now, as I said, like we're actually solving this problem. We can approximate, we can figure out what the rank is with our algorithm, which is achieving relative error. We're getting a 2 to the k squared in the upper bound. So there's a gap here. This gap is related to this problem I mentioned earlier of actually constructing explicit tensors of large rank. Because in these kinds of proofs, what you end up doing is maybe reducing from 3-sat, you end up building a tensor of large rank and an explicit tensor. And we don't know how to build such tensors with rank larger than k. So we don't know how to build k by k by k tensors with rank much larger than k. This is some kind of barrier for improving this. Okay, so any questions? Another thing you could ask is, our running time is exponential in the accuracy. So, but we can get a hardness result in terms of the accuracy parameter epsilon as well. So for rank 1 tensors, already the hardness is there. So if I have a tensor A, and I want to find u cross v cross w, it's a rank 1 tensor. So that the Frobenius norm is at most 1 plus epsilon times opt. What we can show, again, under the same complexity assumptions, is that there's no algorithm for solving this that runs in time significantly less than 2 to the 1 over epsilon to the 1/4. Okay. Now we were getting 2 to the 1 over epsilon when k was equal to 1. Again, this is not optimal, but it is suggestive that some kind of exponential dependence is needed. Okay, so let me just quickly give a slide. Those are our results. Let me just quickly give a slide about the technique that we use to get these bounds. We call it an iterative existential argument, and it works as follows. So I have this n by n by n tensor. The algorithm is really, really simple. Okay, so this is all it does. So I have this n by n tensor, and I can flatten it into a matrix, which is n by n squared. Okay, so if I have an n by n tensor, I can take, say, all the row column faces. Each one is an n by n matrix, and I can put them all next to each other. That gives me an n by n squared matrix. But I could have also taken all the row tube faces and put those next to each other, or the column tube faces. So I can generate 3 different kinds of n by n squared matrices. These are called flattenings of the tensor. Let me call those A1, A2, and A3. They're n by n squared matrices. Then what we do is we choose a random matrix, S1, which is, say, a random Gaussian matrix. It's going to have n squared rows, and it's going to have a really small number of columns. The number of columns is S. It's going to be order k over epsilon. So what's going to happen here is when I compute A1, S1, it takes this n by n squared matrix, and it squashes it down to an n by s matrix with a very small number of columns, right? I'm going to take A2, this other flattening. It's n by n squared. I'm going to squash down the number of columns to roughly, to s again, to k over epsilon. I'm going to take A3, and I'm going to squash it down to k over epsilon columns. And then the argument is just that there exists a good a rank k tensor, which is a 1 plus epsilon approximation, which is in the span of all triples of outer products of columns here, and columns here. So what does that mean? I take one of the columns here. This is a very tiny matrix. There are only S columns. I take one of the columns here. I take one of the columns here. I take one of the columns here. There are only S cubed choices. And each one is giving me a rank 1 tensor when I take the outer product of these three. I look at the span of these things. And that contains a good rank k tensor. Good means a 1 plus epsilon approximation to the best rank k tensor. Okay, so if I wanted a bicriteria algorithm, I'm done. All I do is I know A. I just flatten it in 3 different ways, and I sketch it down to a very tiny matrix, an n by S matrix, and I just take all triples of outer products. That's my bicriteria solution. Those triples, they span a good rank k tensor. That's what so we show this, and I'll show it on the slide, but that's the algorithm. Right, is the algorithm clear? Just flatten and sketch in 3 different ways, and the span contains a good solution. Now, so if you want a bicriteria solution, you can stop. You can optimize it a little bit. If you want a actual rank k tensor, you can do some kind of enumeration inside of the span to find it. And that's why you get an exponential term. Okay, let me get into the details of why this holds. Okay. So let me define opt to be the cost of the best rank k tensor approximating A. Okay? And let me say that U star cross V star cross W star, that is the best rank k tensor approximating A. Okay. I don't know any of these factors. But let me just pretend that I somehow knew V star and W star. So let me think of those as being fixed. This is just a hypothetical argument. Then I can set up an optimization problem in terms of this last factor U. Right? I can ask the question, what is the minimum over n by k matrices U of U cross V star cross W star minus A, that norm? Right? I know the solution. U is U star, right? I'm just setting up this problem. Okay. But the nice thing about this, so the Frobenius norm is just the sum of squares of differences. If I flatten the tensors, instead of being n by n by n, I flatten them to n by n squared, I can just take the sum of squares of differences of these matrices. Right? It's the same norm, right? I mean, so I'm going to flatten A, and I'm going to get A1. Say I flatten in a certain direction. And I'm going to also flatten this rank k tensor. Right? So what am I doing? I'm taking the outer product of 3 vectors, and I'm adding up k of those. Each of those vectors is n-dimensional. Instead of doing that, what I could do is I could take the outer product of 1 vector, which is n-dimensional, and an n-squared dimensional vector, and add up k of those. Right? So what would that be? So instead of taking the outer product of the first column of U, the first column of V star, and the first column of W star, I could take the outer product of the first column of U and the n-squared dimensional vector, which is already the outer product of V star and W star, and written as a long n-squared dimensional row. Why do I do this? Because I take this tensor problem and I convert it to a matrix problem. Right? So instead of this n by k cross n by k cross n by k, I have an n by k matrix, and I'm multiplying it by a k by n squared matrix, where the rows are these n squared dimensional vectorizations of the outer products of columns of V star and W star. I converted a tensor problem to a matrix problem. Clear, everybody? Okay. Why do I do that? Well, now I can leverage all this theory that we have for sketching, for data dimensionality reduction for matrices. So let me say what that means. So I've written this as a matrix problem. I mean, I'm still hopeless because I don't know V star and W star. Let me just call this k by n squared matrix Z1, some unknown matrix. Okay? Now, the main point of this is that what's known for matrices is that if I have this matrix problem, if I choose a random Gaussian matrix S1, and replace this matrix problem by sketching on the right. So instead of this matrix problem, I replace UZ1 with UZ1S1, where S1 is this Gaussian matrix, which is supposed to squash down the number of columns. And I replace A1 with A1S1. I get this much smaller matrix problem. And what's known is that if I solve this much smaller problem, I solve for U, then I get a good 1 plus epsilon approximation to the original matrix problem. This theory of dimensionality reduction for matrices. Okay, but what is the solution to this small matrix problem? You can write it in closed form. Like, what is this problem? This is just a regression problem, right? I don't know Z1, but I'm pretending I know Z1. So I have Z1S1, A1S1, and I'm solving for U. That's just a regression problem. I can write down the solution in closed form. U hat is equal to A1S1 times Z1S1 pseudo-inverse. That's just how you write down the solution to least squares. Okay, but why do I care? I mean, I don't know what Z1 is. I have no idea what this factor is. But what is the point of this U hat? Do people see, like, what was the point of this whole thought experiment? Like, this U hat is inside of the column span of A1S1. A1S1 has a very small number of columns, right? It only has k over epsilon columns. So I didn't need to know what Z1S1 was. I mean, there's some matrix here that makes this rank k. But if I'm fine at stopping with something a little bit larger rank, like k over epsilon, then I'm done. I know A1, I know S1. I just compute them. The column span contains something which is good. Because what this guarantee says is that if I plug in this solution U hat back into the original tensor problem, or equivalently into the original matrix problem, I get a 1 plus epsilon approximation. So that's why we call this an existential argument. I mean, we made this argument without knowing V star and W star, and concluded that there's a good solution U hat in the column span of A1, S1.
That's why you can compute the U from the CURT. So that would be the, those would be the coefficients.
Yeah. So to actually get a rank K tensor, you would have to actually find these things. Let me just, almost done. So that's why we call it existential. Why do we call it iterative? Well, okay, so we found this U hat, so that U hat cross V star cross W star minus A is small, right? That's our good solution. Why don't we just do the argument again? So now let's fix W star and U hat and carry through exactly the same argument. Let's flatten in the second dimension and sketch, let's do A2 and sketch that down. And going through exactly the same argument, what you'll do is you'll find a V hat. So that V hat is in the column span of A2, S2 times something you don't know. And now the approximation is 1 plus epsilon squared because V hat is found with respect to U hat, which you already found. It's iterative. And why don't you do it one more time? Fix U hat and V hat, sketch the last flattening. And now you'll find some W hat, which is in the column span of A3, S3. And this will give you a 1 plus epsilon cubed, 1 plus order epsilon approximation. And so now what's happened is, so you carried through this argument, and now you know there are good small matrices, x1, x2, and x3. These are these unknown, these small matrices you don't know. Z1, S1, pseudo-inverse, Z2, S2, pseudo-inverse, Z3, S3, pseudo-inverse. You don't know what they are. But you can set up this optimization problem. You know that there exists a good assignment, x1, x2, and x3, so that A1, S1, x1 cross A2, S2, x2 cross A3, x3, S3 gives you a good rank K tensor. If you just want a bicriteria solution, you can just stop, right? You just take all, outer products of triples of columns of A1, S1, A2, S2, and A3, S3. You're done. If you want a rank K solution, then you have to solve for x1, x2, and x3. But these are really tiny matrices, right? I mean, x1 is order S by K. It's S by K, so it's roughly K squared over epsilon unknowns. And I have K squared over epsilon unknowns for x2 and x3. I can just set up a polynomial optimization problem. It's going to take exponential time in the number of variables. But fine, the number of variables is small. It's like k squared over epsilon. And so I can actually solve this if the rank is small. Okay, so that's the technique. And let me just wrap up on the last slide. So the goal is to find these factors for tensor low rank approximation. I explained how to do that for Frobenius norm. But there are all these other norms for matrices that we get the first algorithms for tensors. So we can get entry-wise L1 norm for tensors. The approximation factor, instead of being 1 plus epsilon, is poly k, or poly k log n. We can do asymmetric norms. So maybe the sum of the L2 norms of each face of the tensor. Or for tensors, you have more options, right? Maybe the sum of L2 norms of each column of the tensor. Lots of different kinds of robust norms you can look at. We get low rank approximation for those. Again, these are NP hard. They're not going to be 1 plus epsilon approximations. Weighted Frobenius norm, we can get something for that. And no assumptions on the tensor. Input sparsity running time. I want to mention that since our algorithms are based on sketching, taking the tensor, flattening it, and sketching it down in 3 different directions, these are useful for distributed and streaming environments where you see maybe entries of the tensor changing very rapidly, and you kind of need to, in real time, update your sketch, your representation of the tensor. And it's also useful in distributed environments. And finally, just let me mention that these algorithms, the same techniques apply to other notions of tensor rank. So there's what's called the Tucker rank and the tensor train rank. And these other notions of rank are a little bit more well-behaved than the canonical rank that we studied here. In particular, they don't suffer from these border rank issues. And OK, so that's all. Yeah, thanks.
We ran a bit over time. I suggested we take questions offline and have a break for about 15 minutes. We'll be back on time at 10:40.